Hello everyone. Today in this video we are going to understand what are logic gates. Now you know how computers work, but at a small level. But even if you don't know, you need to understand what are logic gates first. At a very microscopic level, you will see transistors in a computer chip. Now these transistors are not there for just show. They are there to perform logical operations. Now these logics are performed by arranging transistors in a way that they make a logic gate. Now, we are not going much deep into that thing, but you should know that logic gates are the most basic thing. Now, your devices such as CPU and your GPU, your SSDs, your RAM all have some kind of logic gates in them. Now, logic gates are digital circuits that take in one or more binary input and give binary output. I suppose that you already know what binary is, but still I'm going to tell you a little bit about binary, which is here. And that's not much about binary, but it will help you understand ahead. So here, binary, as the name suggests, it have two representations. So these two representations are zeros and ones. Now, these 0 and 1s are representing something which is false or low, and 1 is representing true or high. Now, this high or low is the voltage. The low and high is representing the voltage in the circuit, and false and true does the same. So, the logic gates takes these zeros, ones, or low, high, or false and true as input. Now, there are many kind of logic gates, so let us move on to see what kind of logic gates are here and what it does. So the first gate we are going to see is the buffer gate. Now, buffer gate is this looks like a triangle here, and it's taking an input A and giving out an output Y. So for each logic gate, we have a table called a truth table. So this truth table represents the input on the left-hand side and the output on the right-hand side. So a buffer gate is taking input from here, the left, and giving out output Y from the right. So the input in the truth table for A is here it is 0, and the output for input 0 is 0. That's the same. And as the input is 1, then the output is 1. That's the same. So that's the truth table, or not the working, but what a buffer gate does. It gives the same thing as it took in. Like it's like just taking in the same thing and giving out from the other side. So let's move on to the other gate, that is the NOT gate. So a NOT gate gives out the opposite of what it takes. So it's like taking one thing and giving out the complete opposite for it. So say if it takes 0, it will give out 1. As we see in the truth table, if it takes 0, it will give out 1. And if it takes 1, it will give out 0. So the NOT gate is represented by this triangle and with a bubble or a ball in end of it near the output end. So this bubble is doing inversion. It changes the output, like it changes to the opposite of the input. So here, this is same as the buffer gate, but this thing is doing all the work of inverting the input. So for each gate, we have an operation expression which is represented like this. So for NOT gate, it is represented as y is equal to a bar, or y is equal to a exclamation mark a and y. So these are the widely used, this y is equal to a bar and y is equal to exclamation mark a. These are two widely used expressions for NOT gate. So let us move on to the other gate, that is the AND gate. So AND gate takes in two input, unlike NOT and buffer. So these kind of gates, AND gate and the gates we are going to see later, they can take more than two inputs, unlike NOT and buffer gate. So the AND gate provides a true output if only both A and B are true. In other cases, the output is false. So let us see the truth table for AND gate for better understanding. So the truth table for AND gate is here. So for the inputs AB to be 0 and 0, the output is 0, and the input to be 0 and 1, the output is 0, and the input to be 1 and 0, the output is 0, and for 1 and 1 as input, the output is 1. So we saw that even if there is 1, 0, or false, the output will be false, 0. So you can think of it as even if one thing is true, then even if one thing is true, it will give the output as false, because it doesn't want even one thing to be false. You can think of if all the inputs are true, if all one is the input, or true is the input in all cases, then the output is going to be true or 1. And let's go back to see the expression for AND gate. So the expression for AND gate is equal to y is equal to AB, or y is equal to A dot B, or y is equal to A intersection B. This sign is called intersection of A and B. Let us move on to the other gate, that's the OR gate. Now, it produces true output if either A or B are true, else false. So if even one of them is true, then the output will be true. Otherwise, the output is going to be false in other cases. So the Boolean expression for this OR gate is y is equal to A plus B, or y is equal to A union B. Let us see the truth table quick. So the truth table for OR gate is, so here you can see, even if one input is true, then the output is true. And if both inputs are false, then the output is false. So even if one input is true, then your output is going to be true. That's the overall thing. Let us move on to XOR gate. So the XOR gate it looks like OR gate, and it just has one extra line in the end. So this XOR gate's Boolean expression is y is equal to A plus, that plus is in a circle B. Now the truth table for XOR gate is, so for XOR gate, if both of your inputs are false, then the output is false. If both of your inputs are true, then the output is false. So if you have distinct inputs, like the inputs are not same, then your output is going to be true. If your inputs are same, then your output is going to be false. Let us move on to the other gate, that is the NAND gate. This is a little important gate, even though all are important, but this is a bit more important. So expression for NAND gate is y is equal to AB bar. So if you see this looks similar to the AND gate, because it is AND gate, but it just have an inverter or a bubble in the end, which we talked about earlier while studying NOT gate. So this AND gate is a combination of NOT gate and AND gate. It have a NOT gate kind of thing in the end. So its outputs are going to be completely opposite from an AND gate, because we saw the NOT gate inverts the input. So for here, the input will be the outputs of AND gate. For the NOT gate, the input will be the output of AND gate, and the output will be passed through this inverter, so it will be completely opposite. So here we see the truth table for NAND gate. Here it is, both the inputs are 0, then the output is 0. Both the inputs are 1, then the output is 0. If one of them is 1, one of them is 0, then the output is 1. So this is completely inverted version of the truth table of AND gate. So from here we can understand how the NOT gate works, or how the inverter works. Now let us move on to the last gate, which is NOR gate. So I'm just only showing you the representation of NOR gate. I'm not telling you about the truth table or the inputs and outputs of NOR gate. This is your homework, and that's all. Bye.